Hello and Teshidalek to everyone. So in the last class we had completed the topic continuity, in which we had defined continuity and we had seen how we can show or we can check whether a given function is continuous or not. Okay, that can be done in three ways. So first you will check whether the function is defined at the point at which you are checking the continuity. That was the first condition you will look for. Second, you will check whether the limit of the function at that point exists or not, which means you have to check the left hand limit and right hand limit. Okay, and the third condition you have to check is the function value and the limit value in the first two cases should coincide. So then we say that the function is continuous at that point, right? So this is how we check theoretically whether a given function is continuous or not. Okay, so today in this class I will solve few questions and I will show you how you will check whether the given function is continuous or not. Even though the concept is clear, but some of you may face problem in solving questions. So I will help you in that today. Okay, so I will first solve this example. Okay, you look at this example. Find all the points of discontinuity. So points of discontinuity means a point at which the function is not continuous, a point at which the function is discontinuous. So that point is called as point of discontinuity. Okay, so you have to find all the points of discontinuity of f, where f is defined by fx is equals to 2x plus 3 when x is less than or equals to 2, and f of x is 2x minus 3 when x is greater than 2. Okay, so the question can be asked in different ways. Here it is asked to find all the points of discontinuity. The same question can be asked in different way as check the continuity of this function, okay, fx at x is equals to 2, right? Now here you are asked to find all the points of discontinuity, right? Which means throughout the real number set of real numbers, at what point this function becomes discontinuous. So at all these points you have to find the point of whether you have to check whether the function is continuous or not. Okay, so now always remember that when a given function is given in this way, where the function is changing its behavior at one point. So you can see here when x is less than or equals to 2, which means when the x is any real number which is equals to or less than 2. So for all real numbers which are less than 2 and at 2, the function graph is 2x plus 3, is it? So that's a linear equation, so it represents a line. Okay, and line is continuous everywhere, you know. Similarly, now when x is greater than 2, so for all the real numbers which are greater than 2, then the function graph is 2x minus 3, is it? So you can see like this. Okay, now I will first try to explain this graphically. At 2, right, the function is changing its behavior. You can see that for all x which are less than or equals to 2, the function takes its behavior as 2x plus 3. Okay, so the 2x plus 3, when you know this, fx is, okay, fx means it is y, so y is equals to 2x plus 3, which means it is 2x minus y plus 3 is equals to 0. So this is a linear equation in two variable. So linear equation in two variable, you know how to plot the graph. Okay, so when you represent a linear equation in two variable graphically, you will see that it is always a straight line. Okay, so straight line, it is obviously continuous. So which means when x is less than or equals to 2, you will get a graph for this, which will be somewhat a line. So let me just take roughly at this line. Okay, so wherever you take a point here, it will be always continuous. The graph will nowhere broken, so you can extend this how much you want. So up to that you can extend. Okay, similarly, now when x is greater than 2, when x is greater than 2, right, then the image f of x or y is equals to 2x minus 3 is equals to 0, which means it is 2x minus y minus 3 is equals to 0. Again, this is a linear equation in two variables which represents a line. Okay, but these two are different. This is 2x minus y plus 3 is equals to 0, and here it is 2x minus y minus 3 is equals to 0. So the graph will be slightly different. But now the thing is, now when the graph, this function is changing its behavior at 2, we get different possibilities. The one possibility we have is, even though the graph is changing for x less than or equals to 2, the graph is 2x minus y plus 3 is equals to 0, the equation of the line. And when x is greater than 2, then the equation of the line is 2x minus y minus 3 is equals to 0. So the behavior of the graph will change. But the thing is, will it continue? Suppose say if the line changes, if it like this, okay? Now if it happens, then the function is continuous. Even though the behavior or the slope of the line, it changes. But what do we have? The point at this point too, the graph is not broken. The graph is not broken, is it? This is one case we have. So if this happens, then the function is continuous at 2, right? If it is continuous at 2, then obviously at all other points the function will be continuous, because the graph is a line here. So line is a continuous everywhere function, right? So this is continuous everywhere. This is so when you are asked to find all the points of discontinuity, so then you have to check the continuity of the function at those points at which the function is changing its behavior. Only at that point you have to check, okay? Suppose if this happens, then the function is continuous everywhere. At 2 also it is continuous. Rest at all real numbers, the function is continuous. Now the second case it may happen, that is your graph may, okay, up to 2 it is a straight line, okay? So here you may get a graph like this, okay? Then in this case the graph of the function is broken. So in that case you will write 2 is the point of discontinuity. So point of the discontinuity, there will be only one, because for all real numbers which are less than or equals to 2, same graph, so the graph will be a line, so which is continuous. Similarly for all x which are greater than 2, so the function graph, it is again a straight line, so which will be continuous, okay? So now you have to check whether the function is continuous at this point or only, okay? So if this is at this point, if the function is continuous, then the function is continuous everywhere. If at this point the function is discontinuous, then this is the only point of discontinuity. Is that clear? So even though the question is asked as find all the points of discontinuity, it doesn't mean that you will get so many points of discontinuity, okay? So if the function is given in this form, then you will only check the continuity of the function at which the function is changing its behavior, okay? So rest at all the other points the function will be continuous. So you have to remember that, right? Okay, now we will try to prove this, or show, okay, we will try to solve this, okay? Not prove, sorry. Okay, now we will see whether the function is continuous or not, okay? So we will start from this. Now you remember, for checking the function to be continuous, we have to look for 3 conditions. Number 1, f of c should be defined. F of c means c is the point at which you are checking the continuity. In this case, we are checking the continuity at 2. So f of 2 should be a defined value. Is that clear? Number 2, if this happens, then you will go for the second condition, that is limit of the function as x tends to 2 exists. This should happen, right? Okay, if a function is satisfying these 2 conditions, then you will go for the third condition, that is limit of the function, that is left hand limit and right hand limit. This is equals to the function value, whatever value you got at number 1, condition 1. So these 3 things should happen so that the function is continuous. Now we will see whether the function is satisfying these 3 conditions or not, okay? So first of all, I have to find out the value of f of 2. Okay, so we are checking the continuity at, you write it like this, x is equals to 2, okay? So first you find out f of 2. When x is equals to 2, the function, will it take this value or this value? First you have to think, okay? So this is the function, it takes value 2x minus 3 when x is strictly greater than 2, right? So but here in this case we are taking x is equals to 2, which comes in this category, right? X is less than or equals to 2 means this category. So therefore your function will be 2x plus 3, right? So 2 into x is 2, so 2 into 2 plus 3, so that is 4 plus 3 is 7, which is a defined value, right? So therefore the first condition is satisfied, okay? Now you will look for the second condition, that is you have to find out left hand limit and right hand limit. So left hand limit x tends to 2 from left hand side, okay? Now x is tending towards 2 from left hand side means x is less than 2, that I showed you on the number line, okay, in the last class. So when x is tending towards 2 from left hand side, x is very near to 2, but it is on the left hand side of 2, which means x is less than 2. So in that case, your function will be this one. So that is 2x plus 3. Okay. Since it is a polynomial, directly you just substitute the limit point over here. So that is 2 into 2 plus 3. And you remember that when you had substituted the limit point, then you will not write limit. So you will just directly write this. Okay, so this is 2 2s are 4 plus 3, that is 7, right? Then you will show right hand limit, find right hand limit. So that is limit of x tends to 2 from right hand side, positive right hand side. Okay, so 2 raised to positive we write. So x tends to 2 from right hand side, which means x is very near to 2. X is coming towards 2 from right hand side. So which means x is very near to 2, but it is on the right hand side of 2, which means x is greater than 2. So when x is greater than 2, then your function takes value 2x minus 3. Is that clear? So this is how you will choose the function in the correct way. Okay. So this is equals to, now you substitute the value here. So that is 2 into 2 minus 3. Okay. So 2 2s are 4 minus 3. So that is equals to 1. Okay. Now here what do we get? Left hand limit is equals to 7. Right hand limit is equals to 1. So this means left hand limit is not equals to right hand limit. So therefore limit of fx as x tends to 2 does not exist, which means the function is not satisfying the second condition. Okay, if it is not satisfying the second condition, then you don't have to do this third part. So here only you will stop and say that therefore x equals to 2 is the point of discontinuity. So in this way you will conclude. Is that clear? So here you are asked to find the point of discontinuity. So you will write 2 is the point of discontinuity. So only 2 will be the point of discontinuity. Rest, there won't be any point of discontinuity. Okay, so even in question, if it is asked to find out all the points of discontinuity, so you don't think that you will get more than one point of discontinuity. Wherever the function is changing its behavior, at only that point the function may be continuous or may not be continuous. So you have to check the continuity only at that point, even though it is asked find all the points of discontinuity. Okay, so this is just to confuse you. So you will know that whatever the question is, so you will check the continuity of the function only at that point at which the function is changing its behavior. So you will remember that. Okay, so here we got this 2 as the point of discontinuity. Okay, if the question is asked as check whether the function is continuous at 2 or not, then you will write therefore the function is discontinuous at x is equals to 2. So however the question is asked, according to that you have to answer. Okay, so this is one example I wanted to do. Okay, now next I will take one more example. Okay, I told you when you are finding or evaluating the left hand limit and right hand limit. Okay, so if your function is polynomial, then you don't have to do that substitution method. Let h is equals to let x is equals to 1 minus h 0, the substitution method, you don't have to do that. You can directly substitute. Okay, but in case of greatest integer function and modulus function, so then you need to use this substitution method. Okay, okay, now we will take one more example, example 2. Okay, so I will give you this question. Prove that the greatest integer function is discontinuous at all integral points. Okay, prove that the greatest integer function, now you are familiar with greatest integer function. Okay, prove that greatest integer function is discontinuous at all integral points. So how do we write a greatest integer function? We write f of x is equals to, this is the notation we use for greatest integer function. Now this function has been introduced to you in class 11. Okay, So this is how we write a greatest integer function, right? So if we quickly recall, what do we mean by greatest integer function? Some of you may have forgotten what do we mean by greatest integer function. So for them, I will just quickly revise this. Okay, so if you take x, this x is any real number. So for greatest integer function, our function is from set of real number to real number. This is fixed, right? So you can take any real number, okay, and you will get some. If I take f of 1, so greatest integer function of 1 is 1, okay. So if I take f of 2, then I will get greatest integer function of 2 is 2, right? If I take greatest integer function of negative 5, then I have negative 5, is it, right? So which means if you take, if you find the greatest integer function of any integer, whether it is positive or negative, then the image will be itself. If you take greatest integer function of 1, you get 1. If you take greatest integer function of 2, you get 2. If you take greatest integer function of negative 5, you'll get negative 5. So for all the integers, you will get the same image, okay? But since it is a set of real numbers, the domain, so not only integers, you have other numbers also. So if I take, suppose if I take greatest integer function of 1.9, so then greatest integer function of 1.9 is 1. So what you have to do is, if it is in decimal or fraction decimal, so then you have to take the greatest integer which is less than this value. So 1.9, the integers which are less than 1.9, so you'll get 1, 0, negative 1, negative 2, and so on. Out of all this, you have to choose the greatest one, so that is 1, okay. Similarly, if I write f of 7.1, okay, so that is greatest integer function of 7.1. So you have to take the integer which is smaller than 7.1, okay, and nearest to 7.1, so that is 7. So it will be 7. Now if I take a negative integer, say negative decimal, so if I write, say, negative 2.1, okay, so that is negative 2.1. So first you have to select all the integers which are less than negative 2.1. So negative 2.1 less than negative 2.1, so it starts from negative 3, negative 4, negative 5, and so on. So it's like this. Negative 2 is somewhere here, so then you have negative 3, negative 2.1 is here. So negative 2.1 less than integers, so it starts from negative 3, negative 4. So out of all this, you have to choose the greatest one, so that is equals to negative 3, because many of the students do this mistake. They make this mistake. So the greatest integer function of negative 2.1, they choose negative 2, which is negative 2 is greater than negative 2.1. So you have to find the smaller integer than the number itself, and out of all these small integers, you have to choose the greatest one, so which we call it as greatest integer function, okay. So this is how the greatest integer function is defined, okay. Now the graph of the function is also there in class 11. So graph of the function, from there you will easily see that the function is discontinuous. So if we recall the graph of greatest integer function, so this is, say, 0, 1, 2, 3, 4, and here we have 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. This is negative 1, negative 2, negative 3, and so on, okay. So from 0.1, 0.2, 0.3 up to 0.9, its all image is 0. You know that, 0. But when you reach 1, its image is 1. So we have to exclude this point. And then 1.1, 1.2, 1.3 up to so on, all its image is 1. So the graph continues like this. When it reaches 2, its image is 2, right? Greatest integer function of 2 is 2. So up to 1.999, and now we don't know the point which is nearest to 2. So therefore, you just exclude this 2. So remaining all the points we are taking. Oh, sorry, you have to exclude this point here, not this one. Okay. Then for 2.1, 2.2, 2. All image will be 2. And then when you reach 3, its image is 3. So you can, the graph of the function is like this. So similarly here on this side, the graph is like this, okay. This is 0, and you will exclude this. So okay, then you take 1, and then its image is somewhat like this. Okay, so this is the graph of greatest integer function. Now this you had already learned in class 11, so I'm not going in detail. Okay, so now graphically you can see that the function graph is discontinuous. It is broken here, it is broken here, it is broken here, so the graph of the function is broken. Okay, now at what type of point it is broken? You can see here it is broken at 0, it is broken at 1, the graph is broken at 2, 3, 4, -1, it is broken at -2, it is broken at -3, it is broken, right? So the graph of the greatest integer function is broken at all integral points. Now here there's one more term, that is integral point, means the points which are integers. Okay, so here you can see that this greatest integer function is broken at all the integral points, the points which are integers. So it is broken at -3, -2, -1, 0, 1, 2, 3, 4, and so on. So the graph of the function will be broken at all integers. So therefore we are here asked to show that the function, greatest integer function, is discontinuous at all integral points. Okay, so we have to prove this. Graphically it can be seen, but now how we are going to prove? Okay, so we are going to prove this. So with using the same method we are going to do, there's nothing new. Okay, so now you have to look for the three conditions, that is f of, now here we have to check at all the integral points, at not the specific point. So we will prove it in general. Okay, it's not possible for us to show that it is discontinuous at 0 and then it is discontinuous at 1, it is discontinuous. We cannot show that for all integers. So what we will do is we will take help of a parameter or variable a, and let this a be any integer, right? So we will show that this function is discontinuous at a. I'm going to do that. So first of all I will write let a belongs to any integer. Now this a can be 0, 1, 2, 3, 4, -1, -2, -3, and so on. Okay, so you will take a variable integer. Now we will show that this function is discontinuous at a, which means it is discontinuous at all integral points. So why I am doing this? Because it is not possible for us to show that the function is discontinuous at all integral points. One by one we cannot do that. So therefore I'm making this substitution. So for this integer I have taken here variable a, right? Now what you will do is you have to look for those three conditions. So first one is f of a should be defined. F of a is defined, so you should get a defined value, right? And then what we should have is limit of fx as x tends to a exists. That is, left hand limit and right hand limit should be same. And the third one is these two values should be same, that is limit of fx as x tends to a, where a is some integer, is equals to f of a, right? So the method we are going to use is same. We will check for these three conditions. If this function is satisfying these three conditions, then the function is continuous. Is it? Okay, so now we are going to do that. Let a belongs to some integer. Okay, so now first we will show that f of a, so my function fx is, what is it? It is given as greatest integer function. So f of a is greatest integer function of a. Now we know that a is an integer, so for under the greatest integer function, the image of an integer is integer itself. I'd shown you. So a is an integer, so the image will be a itself, which is a defined value. So the first condition is satisfied. Now we will check for the second condition, that is we have to find left hand limit. So this is equals to limit of greatest integer function of x, okay, where x is tending towards a from left hand side. Is it? Now what we are going to do is, we know that a is a integer. A is an integer. Now without using that substitution method we won't be able to solve it, so I'm going to use that. So I will write let x is equals to, now what we have is here this is a and x is tending towards a, is it, from left hand side. So x is somewhere here, so x is less than a, x will be always less than a. So to show that I will write let x is equals to a minus h. We are showing that x is less than a, so I'm subtracting a small number h, positive real number, from a, which means this difference will be always less than 1, okay? And h is the length of the interval. So as x tends to a, h will tend towards 0. As x tends to a, the length of the interval, it will decrease, it will tend towards 0, is it? So I'm going to use this substitution over here. So I get here limit of, now what is my x? X, it is a minus h, and h tends to 0, is it? After substitution I have got this. Okay, now what is this h? H is a small positive real number. It is some small decimal number, positive decimal number, and a is an integer, right? So we are subtracting some small positive integer from a. So then if suppose say if I write this, a is equals to 2, a is some integer, this is just an example, okay? A is some integer and let h is some positive real number. If I write 0.1, so then what is a minus h? So that is 2 minus 0.1, so which is equals to 1.9, okay? So in that case, greatest integer function of a, okay, greatest integer function of 1.9 is equals to 1. So when a is equals to 2, right, when you are subtracting a small decimal number from 2, then the image under the greatest integer function is 1. Similarly, if I take a is equals to 3 and h is equals to 0.1, some small positive real number, not necessarily you have to always take 0.1, you can take 0.01, 0.2, 0.3, any positive real number you can take, okay, but that should be close enough to a. So this is now a minus h, so you get here this is 3 minus 0.1, which is 2.9, okay, and when you take the greatest integer function of 2.9, what do you get? You get 2. So when a is equals to 3, okay, so for a minus h, its image is 2, right? So similarly now, when you take a minus h, so then its image will be a minus 1, 1 less than a. When a is 2, you are getting image 1. This is 1 less than 2, right? When a is equals to 3, you are getting image here 2, which is 1 less than 3. So when it is a minus h, then its image will be a minus 1. That will be 1 less than a. So the left hand limit is a minus 1 when you put here, okay? Then for the right hand limit, okay, for right hand limit, what is so for right hand limit of fx, okay, fx I can directly write that is greatest integer function, x tends to a from a right hand side, okay? So now I'll make the substitution here. In this case, x is greater than a because it is like this. This is a and x is coming towards a from right, and so x will be somewhere here, which means x is greater than a. So to show that, I will write let x is equals to a plus h, where h is some positive real number, which means when you are adding a small positive real number on a, okay, so then what do we have? This x will be obviously greater than a. So just to show that I'm making this substitution, as x tends to a, h tends to 0. H is the length of the interval between them. So as x will move towards a, h will decrease length of the interval. So at most x can reach a. By that time h will be 0. So as x tends to a, h tends to 0. Okay. Now we put it here. So we get here limit of, now what is x? It is a plus h. Okay. X tends to a, then h tends to 0. Right. So now this is equals to, okay. Now when you are adding a small, okay, now I'll show you one example. Let a is equals to 2, h is equals to 0.1. What is a plus h? 2 plus 0.1. So that is equals to 2.1. So now when you take the greatest integer function 2.1, okay, 2.1, its image is 2. So when a is equals to 2, its image is 2, right? Similarly, when you take a is equals to 3, h is equals to 0.1. So it will be 3.1. That is a plus h. So 3 point, so you get image 3, right? So likewise, when you take a plus h, that will be a point something. So its image will be a, the nearest greatest integer function. So that is a. Okay. Now here left hand limit we got a minus 1 and right hand limit we got a. So therefore you will write, therefore left hand limit is not equals to right hand limit. Hence limit of fx as x tends to a does not exist. Therefore the function is discontinuous at all integral points. What is a? A, you are getting this, the limit of the function does not exist at a, which means the function is discontinuous at a. What is a? A a is all integers. So therefore you will conclude like this. So therefore the function, the greatest integer function is discontinuous at all integral points. Okay, so this is the two example I wanted to show you, just to make it clear that how you are going to theoretically show or check whether a given function is continuous at a point or not. Okay, so this is how you are going to do. So now the most important thing is you have to remember these three things. We had defined continuous function. Okay, so with these three conditions you will check if a function is satisfying all the three conditions, then the function is continuous. Okay, now the important part in the three part is showing the existence of the limit. Okay, so now this is the major concept in this topic. Okay, so and that too you had already studied in class 11, so you shouldn't face much problem in this. But still, if you are facing problem, then you check the lesson again, the part 1. Okay, so continuity and differentiability part 1, my lesson, first part. So you go with that and try to understand how do we check the existence of limit. Okay, so if you are clear with this part, then these two are quite simple, so easily you can check the existence of limit. So checking the existence of the limit is the most difficult part in this topic. Okay, so you should be thorough with that, and if you are clear with that concept, then I think continuity is very simple. Okay, so most of you can do it. So you will do this exercise 5.1. Exercise 5.1, question number 6 onwards you can solve. Okay, so from this question onwards you can solve. So that is to check the continuity of the function, or the question may be given as find all the points of discontinuity I had shown you in the previous example. So almost all are same. So in all questions the method of solving will be same. You have to check these three conditions, that's it. Okay, so with this I will stop here. We had completed this topic continuity, and in the next class I will be starting with the next topic, that is derivative or the differentiability of a function. So we'll meet in the next class. Okay, thank you.